Dr. T.V. Geeta, Professor, Department of Computer Science, College of Engineering, Guindy, Anna University. Her special interest, Artificial Intelligence and Natural Language. She has published more than 143 articles in national and international journals. She has guided around 7 PhD students. She has got Young Scientist Award from Government of Tamil Nadu in the year 2000, Chief Minister's Special Mention Award in the year 2002 and Woman of Excellence by Rotary Club in the year 2003.
Welcome to the UGC lecture series. In this lecture we are going to talk about binary tree traversals, some aspects of binary tree traversals, its applications, and then how binary trees are represented in the computer. So let us first look at binary tree traversal. Now we have already seen some traversals before, but here in this we are looking at a general traversal called the Euler-Tor traversal. So here what we do is we imagine walking around the tree. We have seen a little bit of this in a general tree, but we are looking at special, as I already told you, binary tree traversals are important for many applications of computer science. So we are again re-emphasizing the traversal problem of trees with special emphasis on binary search trees, binary trees. So imagine we walk around the outside of a binary tree, then we start at the node and then we move counterclockwise and staying as close as possible to the tree as we go around doing the walk. Each node V of t is encountered 3 times by the Euler, first on the left, that is when you are traversing going from the left, then once from below and once on the right. So how you take, I mean whether you print or list the node when you are on the left or when you are coming from below or when you are walking on the right is how the traversals are defined. So this is like a generic traversal of a binary tree. The pre-order, in-order and post-order traversals are special cases of the Euler tree traversals or Euler-Tor traversal. This is one way of looking at traversals, though in many places we have looked at traversals and we meant as though it was only pre-order, in-order and post-order. There are other types of traversals also like the level by level traversal. So as I already explained, we walk around the tree and visit each node 3 times, once from when we walk on the left, one when we walk from below and one when we walk on the right. So this is how it is said. So you can see that in this node you can walk on the left, you can walk from below and you can walk on the right. So let us first write a pseudocode for the Euler tree traversal in general. So perform action for visiting node on the left. If V is internal, then Euler-Tor V left. That is the meaning of checking whether a node is internal is that we are checking whether the node is a leaf node or a internal node. Perform action for visiting node from below. If V is internal, then you repeat recursive algorithm with V now the right node and perform action for visiting the node on the right. So this Euler-Tor traversal is a traversal in which it is a generic traversal where we visit the node 3 times. So for pre-order traversal, we do only one type of visit, that is the Euler-Tor with the visit only on the left. For in-order, what is it? For in-order, we visit it when we are coming from below, and for post-order we visit it when we are walking on the right. So other applications is like for example computing the number of descendants for each node V. So you can initiate the counter to be 0, increment the counter each time the node is visited on the left, and the number of descendants is you again have the counter initialized to 0 and you increment the counter each time the node is visited on the right and counter when node is visited on the left plus 1. So this is the Euler-Tor. Normally we do not use the Euler-Tor as it is, but it is a basis for many of the other traversals as already explained. Just to repeat, pre-order traversal is Euler-Tor when you walk on the left, in-order is when you walk from below and post-order is when you walk on the right. So this is a typical application of a binary tree, the arithmetic expression. As you know that in computers the evaluation of arithmetic expression is an important algorithm that we go about, and for this normally the arithmetic expression is represented as a tree. This will take care of the priorities of the of the expression of the operators of the expression, and depending upon what notation you want for the arithmetic expression, normally we use infix expression, infix notation. We can also have pre-order notation and post-order notation. So now let us look at an application of the binary tree, which is the arithmetic expression. So the arithmetic expression is given as an infix expression. This is how we normally notate the or represent the arithmetic expression in everyday life. So first we see an A. So when you see an A is an operand. So obviously the arithmetic expression consists of operand and operators. So when you see an operand, you create a leaf node for it. Then you have an operator. So this leaf node is associated with this operator, and then you have B. So that is again a operand, so you create a leaf node over it. Now if you look at this A divided by B is a binary expression, and so you have a binary tree, a small binary subtree for A divided by B, where the division sign or the operator comes in the as the parent, and the two symbols, that is A and B, or the operands, come as children. Next you see an operator. So the operator is put as a parent of the node. I will explain this again, and then you are putting C, which is an operand, so that is a leaf node. Now for this operator star or the multiplication, this subtree is one operand and this subtree is another operand. So now you have completed up to this. Next you see a star, so the star will be put here, and then you have a D. So D, you first create a leaf node and then attach it. So now for this star, this part of the expression, this subtree is one operand and this D is another operand. Now next you see plus, you put plus as a parent, which you have done, and then E is created, a leaf node is created. Now if you look here, for the plus operation, this whole thing is a subtree, this whole subtree is the operand, and this E is the another operand. So in this case we have taken all of the operators as binary operators, and you will see that all the operators come into the tree as interior nodes, and all the operands come into the tree as leaf nodes. So now what is the importance? The importance is, now you, by doing different types of traversals on this tree, you can automatically get the infix expression, the postfix expression, and the prefix expression. And the postfix expression is very important when you are doing evaluation of the arithmetic expression using a computer. So this is the pre-order traversal or prefix expression. So here what happens, we start in another way. You first see a plus, so you put that as the operand, and then you next you see a star, again an operand, child, then you see another star, that is another child, then you see the division sign, again a child, then you see A, put it there, then you see a B, put it in this way, then you see a C, again you put it here, you keep filling the tree appropriately. Now you look at this is not a natural way in which we write an expression, and it is not a natural way in which to construct the tree. So you do not have to construct it, even if you do a pre-order traversal of, this is the original tree we got. So if you do a pre-order traversal, remember a pre-order traversal, you go on till you see a pre-order traversals, you list the node as soon as you see it. So you list plus, then you see, you go to the left, you list this, you go to the left, you list this, you go to the left, you list this, and then you list this. Now you have already taken care of this, next comes B, you have taken care of this, next comes C, you have taken care of this already, D, taken care of this, E. So the pre-order traversal of this tree gives to you the prefix expression. Similarly for postfix expression, I am not explaining this in detail, you can understand how. Normally when we are doing this, we only construct the tree using the infix expression, because it is the natural way of representing an infix expression, and the prefix and postfix are normally converted or got from the infix expression, or conversion from infix to postfix or prefix is done using the traversal of tree. So this is one very important application of binary trees, where we have an infix expression represented using a binary tree, and then that is converted into a postfix expression, and the postfix expression is evaluated using the these both the tree and the stack data structure. So this is one very important application of data structures. This is another traversal which is not seen so often, which is called the level by level traversal. So here what we do, this is the level by level traversal of the tree. So as you can see, this is the tree. Level by level traversal, you start with the root, then traverse this level, that is star and E, then traverse this level star and D, this is star and C, and then A and B. This is not and normally does not come within the Euler's tool, which we have seen in the previous. This is a special case of level by level traversal. This is required in some applications where you want to take care of the levels before you go down to other things. This is an example of when we do breadth first search, where we want to consider the children before we go further. So this is an example of level by level traversal. This does not come in the Euler 2 traversals. So this is the in order. This is just a simple algorithm for in order traversal. So you in order to the left, then print the data, that is, and then in order to the right. So this is the in order traversals. Pre-order is you first print the data, then go to the left, recursive algorithm, then go to the right. This is post order. So you go to the left, go to the right, and then do the listing of the data. So these are the three traversals which we have already seen for general trees. We are just applying it to binary trees. It is in fact simpler in binary trees because we have only 2 children. Now let us look at another interesting operation of binary trees. We have seen already one, that is the evaluation of conversion of infix expression to prefix and postfix, and also the evaluation is easier using postfix. Now a variable is an expression, and if an x and y are expressions, then this is how to define a propositional calculus. Not x, this stands for negative, x intersection y and x union y are expressions. This is a negation, this is the intersection, and this is the union. So parenthesis can be used to alter the normal order. Normally this has more precedence, that is negation has more precedence than intersection, and intersection has more precedence than union. But if you want to alter that, for example x1 or x2 intersection not x3, normally this will be done first, then this will be done, this will be done. This is anyway it will be done in this order only. Okay, but you can use parenthesis to change the order if you want. So suppose you put the parenthesis here, this will be done first before we go along. So this is an example of the propositional calculus expression. This is similar to the arithmetic expression. Only difference here is that we, in addition to having binary operations, we also have a unary operation. For example, these negations are all unary operations, which we did not see in the previous example of arithmetic expression. So here you have first you have x1, so a leaf is created, then you have intersection, so that is created, then you have a not, so a not and x2, this subtree corresponds to this, and this is created, and so on. So you can do post order traversal to get the postfix evaluation and so on. So again level by level we will just look at the algorithm. As I already told you, we do use a queue here. In fact queue is one method of doing breadth first search, and one data structure required to do a convenient way of doing a breadth first search, and level by level uses a queue for doing the level by level, in other words is a breadth first search, and so it uses a queue. So this is an example of how the queue is used to do the breadth first traversal. So with that we have finished the first part. So now let us take a small break. Okay, now let us continue with the lecture. Now we are going to talk about binary tree representation. We have seen many operations on binary trees, but in order to do these operations we need some representation of the binary tree in the computer. So again, just to look at what a binary tree is, before we decide on how to represent it, it has a complete binary tree. Suppose it is a complete binary tree with n nodes, then the depth is log n plus 1, and this is represented, you can represent this sequentially and using an array. This is only if the tree is binary tree is complete. Only in this case the sequential is applied. I will tell you why later, and it is represented sequentially. Then for any node with index I, where I is varies between 1 and n, we have parent of I is I by 2, and of course I is at the root, and if it has no parent, then obviously you cannot define a value called parent of I. Then left child is at 2I, and but if there is no left child, then of course you won't get left child, and right child is 2I plus 1. If I plus, of course both these cases you will have to check whether 2I and 2I plus 1 is less than or equal to n. So otherwise it has no right child. So here by just giving indexes and calculating mathematically, you have parent of I is I by 2, left child is 2I, and right child is 2I plus 1. So this is a representation, a simplest representation of a binary tree. It is a very effective representation also if the tree is a complete binary tree. The problem is that most binary trees are not complete binary trees. Then what happens? You have lot of gaps in your sequential representation, and it is not a very efficient way of representing. So this is an example of a sequential representation. If you look here, this is a specific application or example of the tree where it is skewed completely, opposite of complete binary tree is taken, so that it will show you what we mean by this. So you first have the root node at 1, then if you remember 2I is the left node, so 2I, 2 into 1, 1, and C is at is the child of left child of B, and B is 2, so the left child of B will be at 2 into 2, which is 4, and then this has no right child, so no question of 2I plus 1. Then C is now at 4 and D will be at 4 into 2, 8, and then E is at 2 into 8, this is 16. So if you look at this, out of the 16 locations you are occupying only 5 locations. This is a very simple example that we have taken as a sample, but suppose you have a tree, and this is a very skewed example also, but suppose you have a tree with 100 nodes and the 100 nodes are skewed, almost skewed, then you will have 100 nodes, and it will come to many more locations you may have to have in order to represent this. So this leads to waste of space, but only advantage of this is that the application will, this particular representation will allow you to directly access the nodes. It is a using indexes. That is the advantage of this array representation of a tree. So this is another example of an array representation where we are assuming an almost complete tree. If you look at this, we said that for a complete tree it is very good. So let us look at a complete tree. It is not a full tree. You remember the difference between complete tree and full tree. Complete tree means all nodes in the binary tree as either a 0 number of children or 2 number of children, and so this is an example of such a complete tree. So if you look here, this is the parent, its child is at 2I, 2 into 1 and 2I plus 1, 3. Then if you take this 2, I is 2, 4 and 5, 2 into 2 plus 1, and then this is 3, so it is 6 and 7 that we have here, and then this is D is 4, so it is 8 and 9. So this is an example of a binary tree, complete binary tree representation. So I said that for a complete tree there is no wastage of space. Then why is sequential representation not used for even complete trees? The reason for this is that even though there is no wastage of space, if you want to insert a node or delete a node, then you have to shift all the nodes down or up respectively. If you want to insert, you have to shift all the other nodes. Suppose we want to insert a node as a child for say B, and this has to go down, then everything has to be shifted. Similarly, if you want to delete, everything has to be up. The problem is similar to what we have already seen about arrays, where in arrays insertion and deletion are inefficient, but accessing is very, or searching for a node is very efficient. The same is true for sequential representation of trees, because we are using array as the representation. So now let us look at implementation of binary trees. So this is exactly what we have already seen. A sequential structure for binary trees is based on the following way of numbering the nodes. For every node V of t, P of V is the integer defined as follows. If V is the root, then we say P of V is equal to 1. If V is the left child of U, then P of V is equal to 2P of U, and if V is the right child of node U, then P of V is equal to 2P of U plus 1. This we have already seen 2I, instead of using I we are using P here. So that is the implementation, and this is the example of that. So this is a full and complete binary tree. So if you look here, you have A at 1, B this is the child, and C, so 2 and 3, this is 2, so this is 4 and 5, and this is 3, so this is 6 and 7, this we have already seen. So the operation is size is empty, it will take only, you can easily find because you know the size of the array. Positions element, this is difficult. Swap and replace also is easy. The only problem is for insertion and deletion, finding the root, finding the parent, finding the children, finding the left child, finding the right child, knowing whether it is internal or external, if it is the root, expanding the external, expanding the external and removing from the external is also fairly easy. So, but however, as because of the disadvantage that we saw where there is inefficiency in insertion and deletion if you are using sequential representation, and also because the representation if it is not a complete tree, many cases you can't guarantee a complete tree, then the representation is also results in waste of space. So we go for the more natural representation of a binary tree, which is the linked representation. So here you have a node which has the data, and you have a pointer, left pointer pointing to the left subtree and a right pointer pointing to the right subtree. So this is the structure T node which consists of the data and 2 pointers to the left and right subtrees. So this is a linked structure of so you have a root, and then here you have the left subtree, here right subtree, left subtree, right subtree. Obviously the left and right pointers will have a null value if there are no left child or right child. So this is the time taken for the operation that we saw before. You will see that only for position and I think it is 0 to n, all the rest the time is of the order of 1. So this is the recursive definition of a node which we have already seen, that is a node of a tree, and this is the tree definition. So, so a node is represented in some representations that we saw even before, which I did not tell at that point of time. You have additional, you have a node consisting of 4 parts. One part is the data, okay. One is the left subtree pointed to left subtree, the other is the pointer to the right subtree. In addition, you also have a pointer to the parent. Now there are certain applications or certain operations that you have to do on trees where such a pointer to the parent is also very important. So there are certain representation which use 3 parts to represent a node in the linked structure, and the other one you use 4 parts. So if you look at this tree, you have B as the root, so this is the data element, and the parent, since it's the root, is null, and the left points to A and the right points to the node in which D is there. Then if you take A does not have any children, so the left points to 0, right points to 0, this is the data, but you have a pointer to B. Now if you take D, it has both children and it has a parent, so you have a pointer to the parent, you have D, you have the pointer to the left subtree, pointer to the right subtree. Leaf nodes will have left and right pointer 0 as before. So this is a different representation for the binary tree. It depends on how efficient you want all operations on the binary tree to be. So this is an example of a C++ implementation of a tree. So you have classes representing tree, and you have constructs, you have update methods, and you have print methods. Print methods are normally used for traversals, update methods are used for insertion and deletion, and constructors are used for constructing the tree. So example of updates include expand external and then remove above external and so on. So this is an example of expand external where you are expanding the node, leaf node, to point to 2 subtrees, and this is remove external where you are removing the node B from the whole data structure. So now let us look at some problems. Assume that you are given a binary tree, and the representation you are given this expression. Please note I have put some brackets here, so you must be careful of how you construct the binary tree. So how do you go about constructing the binary tree? You create a leaf for A, you create a leaf for B, and then this is the operator. So A and B will consist of a subtree whose root is B. Then you should not go here because you have a bracket. So you create a separate subtree for C minus D, where C is one left subtree, D is the right subtree, and minus is the root. Similarly, you construct another subtree for E plus F. So you have 3 separate subtrees. Now this subtree then you take star, this is a left subtree of the subtree of created with A plus B is a left subtree, C minus D is the right subtree. Then you take this, for this whole subtree of created is the left subtree and this is the right subtree. So, this when you are doing with plus you have to use a slightly different method. Then I have given you another example where the tree that you have created in question 1, you traverse it using in order, pre order and post order. If you traverse it in order, you will get the infix expression, which is you should normally get this expression. Pre order you will get the prefix and post order you will get the postfix expression. And you can also try to write a code to traverse a binary tree level by level. Remember, this also uses the queue for doing it. So, you write a complete algorithm using doubly linked list, but try to use a doubly linked list which has a pointer to the parent also. So, in this lecture what we have done is we have spoken basically about binary tree traversals. We have taken a generic case of traversals called the Euler traversal, and then we have tried to tell you how the Euler traversal special cases leads to in order traversal, pre order traversal and post order traversal. We also saw 2 applications of traversals, the arithmetic expression and the propositional calculus expression calculation using binary trees. Then we looked at binary tree representations. We looked at how sequential expression representation or the array can be used to represent a tree, and we saw what the advantage was. Search was the basic advantage, ease of search or efficiency of search. However, there was wasted space and inefficiency in insertion and deletion. So, they went in for the doubly linked list where you have 3 parts to the node, the data, the left pointer and the right pointer. There is also another representation which has left pointer, right pointer, also a pointer to the parent. This seems to be a little redundant, but is used for increasing the efficiency of the node. So, thank you.